Okay, I'm just waiting for some people to come in. Depending on who's coming in, but okay, I think I'll get started. All right, welcome back to STEM Online Academy. My name is Jason. And for those of you who already know me, you know what I'm about. For those of you who don't, this is a math and physics channel where we hope to make undergraduate students fully equipped in their mathematical toolkit, right? One, by giving them the mathematical methods, and two, developing strong mathematical intuition so they can thrive in future careers, and also not just their careers, but in their rigorous thinking framework down the road. So what we're going to do today is office hours. So what that means is, if you see my other live video, we're going to be continuing on with some challenge problems that I assigned. We're going to look over them. Even if you didn't see my last live video, if as long as you have a foundation in integral calculus and linear algebra, you should be able to handle these problems. At least if you've seen some of the theory behind it. You don't need to really know it in detail. As long as you know the theory, you can apply your mind to these problems, okay? So we're going to leave off from Wednesday's gamma function deep dive. I like to call it. That was the title that I gave the last live show. Okay, and we're going to take up the viewer research problems. Okay, and then we're going to extend them in this live show to something called the beta function. Okay, I've talked about the beta function before, but this is going to be in a more rigorous detail. Okay. I want to review some topics that I've talked about before, especially in my book, Advanced Integration Techniques, because it's not good enough to see it once. Quite often in math, you need some regurgitation of the abstraction in order for it to stick, right? Quite often to develop mathematical intuition is a sixth sense, I like to call it, and it takes a lot of repetition and relooking at theorems, definitions, and doing the problems. Okay, so I think what we're going to do is we're going to get started. All right, so let's get started. All right, let me share my screen. Okay, just give me a moment here. Hang on tight. Okay, we're going to go to the whiteboard. Okay, so as I said, this is a mixture of office hours and research level problems. So Fridays is mainly research level problem day. Okay. All right. As I said, as long as you have a background in integral calculus and linear algebra, regardless of how advanced the problems are, you should be well equipped to tackle them. I will refer to some definitions if you don't know them. Okay. So we're going to look at Wednesday's research challenge problems, right? Two, we're going to introduce something called the beta function. Okay, that's an extension of the gamma function. And I'll go into more rigorous detail. Three, probability and physics applications. That will be some stuff there that might be interesting, especially for those of you who like seeing math in a more applied setting. Okay, that's another unique my unique perspective to this channel is that, yes, it's advanced math, but I like to put in applied math as well. Actually, this book is somewhat heavy on applied mathematics. Okay, so it's not just theorem and proof. You will see interesting stuff here that makes the math come alive. Number 4, I should say viewer research problems, new viewer research problems that we're going to be taking up. For some of the audience, I know some of the audience may be interested in this section, so especially on Fridays. I've done some research. Fridays is a research day. Quite often you get research level individuals coming into the live stream. Okay. All right, so let me just get back here. And I probably should put, what else was on my menu? I think I want to put something else on the menu. Those 4 things. There's one more thing on the menu I wanted to mention. And that is, let me see. Let me see here. I was thinking about putting in, no, that wasn't it. Okay, the timestamps. Oh yes, more Q&A, right? These are all Q&A, question and answer, right? So you can ask me, it's a live show, right? So you can ask me questions and I'll answer them. Anything on the material present. Let me see. Also, yeah. So I think we're going to do, yeah. So number 5, I'm going to also mention at the end of the live show about my book. Okay. Plus tutoring. Okay, book and tutoring. And yeah, I'll get into that later. Okay, so let's look at some of the stuff from Wednesday's research challenge problems. Okay, so those of you who have seen my live show, as I said, you know what research problems I'm talking about. Okay, if you watched the last one. For those of you who don't, but are somewhat familiar with the gamma function, then you should be fine. Even if you're not, you can always ask me. Don't be afraid to ask. Again, as long as you have a foundation in integral calculus and linear algebra, you should be fine. I'll give you the definition, and then you should be able. I'm going to help you to reason through the problems, okay, to the best of both of our abilities. Okay, so the problem that we were looking on Wednesday, okay, was finding the asymptotic expansion of the gamma of z plus 1/2 divided by gamma of z. Okay. All right. So we're looking at an asymptotic expansion. Okay. So what is an asymptotic expansion? Does anyone know? Anyone in the chat know about asymptotic expansions of what's of any relevance? Does anyone know what an asymptotic expansion is? Put thumbs up in the chat if you do. If you're not familiar, I can give you some background. Let me see if anyone's in the chat. Answering. Right, so asymptotic expansions. Okay, there's 3 types of expansions, asymptotic expansions. One that uses Laplace's method. Okay, Laplace's method. I might go on to another page here a little bit. Yeah, just give me 1 sec. Yeah, I'm gonna have it down in my notes. Some of the theory that I need to put here if I decide to put it. I think I needed to, but I'm not getting any response. So I'm assuming that nobody knows what an asymptotic expansion is. Okay. So we're going to have to make a new page here. Okay, so asymptotic expansions. I made notes of these. So asymptotic expansions. All right. So method number 1, okay, for an asymptotic expansion. Okay, so let's see here. I'll just say, yeah, method. Well, first off, I should mention an asymptotic expansion. Asymptotic expansion definition. Okay, so definition, an asymptotic expansion is a way to make, let me see if anyone's in the chat. Yeah, and to make interesting approximations. So you see here, approximations of both large, that looks like an H, sorry about that, guys. Both large, I'm going to capitalize this, large arguments. We have a large argument. For the new audience here that's coming in, as long as you, as I said, if you have a background in integral calculus and linear algebra, you should be fine. I do, but since you're new coming in, I do have to give you some definition slash, definition methods type of way of, doing math theory, as a lot of you are familiar with. Okay. Before I go into actually doing the problems, for those of you who have already seen the problem from last time, you probably don't need, maybe you do need a referral from the theory, but the theory is always very important. I can't get away from the theory. Okay. So whether it's applied, pure, or real math, the theory is something you cannot detach yourself from. Okay. Have to go through it. So when you have an asymptotic expansion, right? It's a way to make interesting approximations of both large arguments, large argument functions, and also, and also, I might as well use white here, and also, let me see how I'm going to phrase this. Let me think. How should I phrase this? And also, basic arguments as well, and basic arguments. Okay. And it helps us tell us, like, asymptotically what's happening to models, mathematical models, graphs, and stuff like that. Okay. Any questions? Please give me questions in the chat. Okay. If you have any misunderstandings so far, it's a live show and it's office hours. So please critique me or give me questions of some sort. Okay. Now, if not, I'll go to method 1. Okay, so method 1. Okay, so method, I'm going to highlight this. It's going to be in blue. Method 1. Okay, method 1 is Laplace's method. Okay, so Laplace's method. Okay, not to be confused with Laplace transforms. They look the same. It's true, but they don't have the same function. Okay, so method 1, Laplace's method. Okay, so Laplace's method is the following. Okay, right. So take an integral. Okay, so it's usually written in this form. Okay, so I'm going to highlight this. For those of you who love integrals, you're in the right place. Okay, so I is an integral as a function of s. Okay, and it's equal to the integral of e to the negative s f as a function of x and s ds. Okay. All right. So we use this method only when we're dealing with integrals. What I mean is, if you want to find the asymptotic expansion of an integral, if the question says that, then you would use this type of formulaic approach. Okay. Right. So this is what you'd be using. Okay. So note. Okay. So note. I'm going to put it over here. note, okay. Might use a different color, green. So note, that you only use this integral, right? Only we use, put it in blue actually. We only use this integral method. I'll just say method. This method. Let me use method. Method when we're asked. That's what I say, when we are asked to find the asymptotic expansion. So asymptotic expansion of an integral. So then you use method 1, if that makes sense. Any questions? Okay, so that's when we have looking for an asymptotic expansion of an integral. We're going to use this approach. Quite often, we may need to use integration by parts or some other way to make the integral more friendly or simplified. Right, so note number 1. Okay, that was number 1. Note number 1. Note number 2, maybe. Yeah, so note number 2. I'm just making notes here on the theory, right? So note number 2. Often we will have to use IBP. So often we will use IBP. IBP is integration by parts. Okay, so those of you familiar with it, IBP. Okay, in order to simplify. Why am I saying IBP? Usually integration doesn't, we don't have to, we use a method depending on the situation. The reason why is because quite often if you have a product, you have to use a chain method of some sort. So quite often IBP comes up, but it's not always the case. You can still evaluate the integral without using IBP. Okay, all right. So that's method 1. Just giving you some back history here. If anyone has questions, this is Q&A. Note for anyone coming in, this is office hours. Okay, to be really effective and understand what I mean by office hours. This Q&A on the last Wednesday's homework problems and the theory from last class. Okay. All right, so we're going to continue here. So often we will use IBP. Okay, so integration by part. Okay, so that's this is method 1. Okay, now we have method 2 as well. Okay, so method number 2. I'm going to explain what that is. Okay, so method number 2. Okay. My method number 2. This is called Stirling's approximation. Okay, this is Stirling's approximation. Stirling's, just giving new people who are coming in some back information on the theory that's involved. In case you haven't seen the live show from last time, Stirling's approximation. Okay, Stirling's approximation. And there's 3 points to Stirling's approximation. Okay. There's 3 cases from what you should remember. Okay. So Stirling's approximation, part 1. Okay, so we got the gamma function of x plus 1. I'll explain what this is asymptotic to root 2 pi. Okay. Root 2 pi by x. Okay, parenthesis x all over e to the power of x. This is a basic form. Okay. Right. So x all over e to the x. This is called the basic form of an approximation. Now you're probably wondering when do I use these? You use Stirling's approximation quite often when it's not an integral form, and more likely it's in the form of a gamma function. And when I mean a gamma function, I usually mean either some functional equation that's in terms of a gamma. Okay. All right. So this is the basic form. Basic form. Make my writing better. Sorry about that. Basic form. Again, anyone coming in, this is office hours. Okay, it's your chance to give me question and answers on last lesson's live session on the gamma function in more rigorous detail. There were challenge problems. Okay, so basic form. I guess this is its basic form. Gamma of x plus 1 is asymptotic to root 2 pi x times x over e to the x. This is the basic form. Okay. Then we also have this guy over here. Okay. I'm just forgetting this one. Okay, so this is when you have for very large arguments, gamma of x plus 1 being asymptotic to root 2 pi x or 2 pi z. Sorry, this is supposed to be in z now. Z plus 1 asymptotic to root 2 pi z times z all over e to the power of z. All right, so z all over e to the power of z, right? And then after, it's an infinite series of 1 plus 1 all over 12 z plus 1 over 288, 1 over 288 z squared. Then it alternates. This is not an alternating series because it's not changing each sign each time. Squared minus dot. Okay, this is for large arguments only, right? So this is for very large arguments. Okay, that's a very large arguments. All right. Anyone coming in? Let's see. Oh, hi. Just another Indian guy. I think I've seen you before, just an Indian guy. Can't remember. Hello. I remember you. Did you, were you in the last live session? Can't remember, just another Indian guy. There's quite a few people that I get confused with. I think so. I think you're also another, I've had you before. I'm glad you are enjoying the content to come back in. Right, today is office hours. We're just taking up some of the challenge problems that I posted from last lesson. Okay. Right, so from my book. I was here for one of the streams last week, I think, about the gamma beta function in 5 minutes. Yes. We're continuing on that stuff. So if you enjoy that, this is going to be in more rigorous detail. I forget, are you in, I can't remember, was it university or high school? Just another guy, let me know. Now we're talking about asymptotic expansions of beta and gamma functions. I'm a uni student first year. Oh yeah, so this would be handy. To some degree, yes, this is going to be handy as a computer science major. Yeah, this would be very handy. All right. So yes, yeah, we're going to be looking at continuation of the gamma function and the beta function in more detail, which means it'll be harder. It'll be more proof oriented today. Okay. Yes, even integrals, even though they're applied, they can have their own rigorous proofs and theorems and stuff like that. Okay. It will be handy for computer science because you guys do proofs as well. Okay, so you'll understand the type of arguments I'm going to be making, hopefully. So yeah, so we have gamma of z plus 1 is asymptotic to root 2 pi z, z over e to the power of z, and then multiplied by an infinite series expansion. That's what we have here. Okay. All right. And then finally, method 3, I'm just going to go through this fast. Just pulling up some theory on the asymptotic expansion because it seems like people didn't know about the asymptotic expansion for the problems that I'm going to be doing. Okay. And I'm going to be taking up method number 3. Okay. This one is interesting. All right. So gamma of z plus a. So if you have a gamma function in this form, gamma of z plus some number a is a real number, okay? It is asymptotic to root 2 pi by z. I always forget this one. It's like z minus a half. Z plus a minus a half. Z plus a, just 1 second, guys. Z plus a minus 1/2, half minus z, and then minus z, e to the minus z. I always mess it up, e to the negative z. And then multiplied by 1 plus a by a minus 1 all over 2z. And then after is plus ... Okay. Looks almost like a binomial. If you notice this, it almost looks like it's a replica. It's not exactly a binomial expansion, but yeah. Okay. All right. So we're getting this guy over here. We're going to use one of these methods, either the Stirling approximation or Laplace's method. Okay. So let's tackle problem 1. That wasn't it. Where were we? I was looking at it in a second. Just 1 sec. Yeah, it was finding the asymptotic expansion of gamma of z plus a half divided by gamma of z. Okay. Now that we know how to do asymptotic expansions, sorry about that. That wasn't it. That's for later. Okay, where are we? Nope. I'm always losing my stuff. Sorry, guys. Where was I? Yeah, over here. So the way to do this, does anyone have any guesses on how to do the asymptotic expansion? Remember, this is a question and answer period based off of Wednesday's live session on the research problems of the gamma function. Please let me know, guys. Okay. Tell me your thoughts. Okay, we're going to get into this right now. Okay, so if no one has any clue, no worries. I'm going to walk you step by step based on those definitions and methods I put on the board. Okay, so the solution to this, right? Calculate the asymptotic expansions individually in the numerator, then the denominator. Okay, so gamma of z plus 1/2 is the very last formula that I just put on the board, right? Root 2 pi times z outside the square root, all to the power of z plus a, minus 1/2 times e to the negative z, all in parentheses, 1 plus a times, in parentheses, a minus 1 divided by 2z, and then plus dot, some sort of infinite series. Okay, that's what we have to use here because this is in the form of z plus a, where a is 1/2. Does that make sense? Okay, should make sense. I just put that formula on the board, right? This is using Stirling's method because of the fact that this is a large value, not a large value, a large argument. Anytime when you have a gamma functional equation, yeah, you're going to be using Stirling's method of some sort, one of the three methods that I was mentioning about. So here we're going to do gamma of z plus 1/2. Okay, so z plus a half would be root 2 pi times z to the power of all power of z plus a half minus 1/2 times e to the negative z, parentheses 1 plus 1/2, parentheses 1/2 minus 1, all over 2z, where a is 1/2. Okay, I think that is straightforward. All right, so Stirling's method. Okay, and then we just clean it up. It's this algebra after, right? So continuing. All right, so any questions? Not yet. Okay, so hopefully I have you guys engaged. All right, so for those of you who like advanced math, you're in the right place. All right, so this is gamma of z plus a. Okay, z plus a in the parentheses. Now, as you can see here, all I'm doing is I'm cleaning up everything. I'm saying root 2 pi times z to the power of z. Why am I saying that? This cancels. 1/2 and negative a half are canceling. Okay, so gone, gone. So it's now just left with e to the negative, z to the power of z. Z to the power of z. That was corresponding to this z here. Z to the power of z. 1/2 and 1/2 gets canceled. Then it's multiplied by e to the negative z. Okay, then all in parentheses 1 plus 1/2 times negative a half all over 2z plus dot, 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 dot. Okay, and then we're just continuing on, right? I completely make sure to clean up the algebra here. So this becomes root 2 pi times z to the z, e to the negative z, 1 minus 1/4, 1/2, 1/2, divided by 2z. Okay, and then finally we get our final solution of gamma of z plus a half being approximately equal to, or asymptotic to root 2 pi times z to the power of z, e to the negative z, times 1 minus 1 over 8z plus dot, dot, dot. Okay, so we're just applying the method. It's a formula, not too complicated, if that makes sense. Okay, and hopefully that's, hope you guys are understanding, right? Okay, so we've taken care of the numerator. Now we have to deal with the denominator. Okay. Now the denominator, okay, the denominator can be solved. Think about that actually. Using my judgment to the best of my ability. Yeah, because this was a gamma functional equation. So I'd say also the denominator also would be behaving that way. Because we're using, it's already written in the form of a gamma function. I don't have to I can always use the gamma function integral, right? As all of you know, right? Just to refresh your memories. Okay. All right, so definition, the gamma function. So I'm going to put it here. Put it here. I'll put it over here somewhere for those of you who need to refresh your definition. Right, so definition of the gamma function. I could have just used this definition, right? The gamma function, the gamma function, which will be denoted as gamma of z, right? Gamma of z, okay, is equivalent to the following, okay? Gamma of z equals the integral from 0 to infinity, right? 0 to infinity, x to the z minus 1, e to the negative x dx, where z is a complex number, is a complex number. Okay, this I could have just used that in there, and then after just use Laplace's method as well. Where was it again? What was my problem? It was back here somewhere. Gamma of z. Where were we again? Gamma of z. That was page 1. Yeah, page 1. This guy over here, right? Yeah, for gamma of z. I could have done that for both. Input z plus a half and this for the gamma of z of the integral form of the gamma function, and then doing the same thing for the gamma of z, integral form of that, and then use Laplace's method, which is just saying if you have an integral in the form of a gamma function of e to the negative s power times f of x comma s, then from there you can use integration by parts. You have to, because the gamma function is a product. Okay, and then reduce it from there. It can give you an asymptotic expansion. Okay, so I hope that makes sense. Or you can just use Stirling's method. I just wanted to use Stirling's method. All right. So we have that. Where were we? So I did the expansion for the numerator, the denominator, gamma of z. Where were we? Gamma of z. So we had that, gamma of z plus a half. Okay. Gamma of z plus a half. I did that part. Where were we? No, that isn't it. I'm so sorry, guys. I lost track of where I am. No. Z plus a half, I have that one taken care of. Gamma of z, I believe I wrote it down earlier when I was doing this. By the way, anyone new coming in, this is office hours, right? So office hours corresponding to Wednesday's, that means 2 days ago, live lesson on the rigorous form of the gamma function, and pretty much more in detailed properties, and yeah. And we're doing challenge. I assigned for challenge problems. So if anyone from last time took down those challenge problems, we're taking them up today. Okay. Right. Now for the denominator, I could use this. I'm going to use the root 2 pi z to the z plus a to negative 1/2 e to negative z again, where a is going to be 0. Right. So what should happen here, right? What should happen here for my gamma of z is that everything will cancel except for the z to the 1/2, right? Because think of it having it as root 2 pi z to the z e to the negative z times 1 minus 1 over 8z divided by root 2 pi times z, minus a half, e to the negative z, root 2 pi e to the negative z. It cancels. I'm left with z to the 1/2. So in reality, this comes down to being root z, parentheses, 1 minus 1 over 8z. So 1 minus 1 over 8z plus dot, dot, dot. Okay. Using Stirling's approximation. Okay. That will be the answer. It's very straightforward. All right. Hopefully, any questions on that? Anyone have questions? Okay, so far, no. All right, so we've taken care of the research problem number 1. What was number 2? Let me see here. That was page 2, page 3, page 4. Just give me a sec, guys. How is everything a bit out of whack? Okay. Could have sworn I had it here. Yeah, so we talked about Laplace's method. So again, I'm just reiterating for anyone new coming in. We were talking about doing the research problems from Wednesday. Quite often, most of them had to do with asymptotic expansions, mainly of the gamma function, right? Different expressions of the gamma function. Okay. All right, so this is what we have right now. Method 1, method 2, and method 3. Trying to find where I was again. Oh yeah, there it is. Yeah. So step 2. This is what I meant. Okay. Cleaning up the denominator. Again, I'm looking for gamma of z. It's asymptotic expansion. A being 0. The asymptotic expansion would be root 2 pi times z to the whole power of z plus a minus a half times e to the negative z, and then parentheses 1 plus a by a minus 1 divided by 2z plus dot, dot, some type of infinite series product, right? Okay, so Stirling's approximation, a is going to be 0, right? So it's just algebra. Okay, and what you should see here is that you get an asymptotic expansion of root 2 pi times z to the minus a half e to the negative z times 1, and then this is over here. Okay, so that's my gamma of z expression. Since we're dividing the ratios, it's the ratio of the approximation, of the ratio of the asymptotic expansion, sorry. So take both asymptotic expansions, divide them. You're just left with z to the negative 1/2, bring it upstairs, becomes positive. as n to the 1/2, parentheses 1 minus 1 over 8z plus dot, 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 and then you just get root z by 1 minus 1 over 8z. Okay, so I actually want to see, I've written it on the board so you guys can see it. Let me know if the algebra is an issue, please. Okay, it's not an issue. All right. Hopefully that made sense for research problem number 1. Okay. All right, so again, anyone coming in, this is office hours on research problems from Wednesday's live show. Okay, live show was on gamma function, the deep dive. So pretty much a more rigorous approach, more rigorous problems on the gamma function from my book. Okay, advanced integration techniques. All right, so we're just leaving off from there, right? So the homework problems I assigned, and then we're going to go into the beta function in more detail. Okay, so number 2, it was this problem. It was finding the asymptotic expansion of this integral. Let me see if anyone's coming in. Okay, so nobody else yet. So we're going to look at finding the asymptotic expansion of this integral here. So the integral over r, and it was e to the negative x squared over 4t times f as a function of x and t dx. Okay, and it's over the reals. What I mean, the integral is over the reals. Does anyone know what that means? What are the limits of integration? So let us know that. What are the limits of integration? This should be on my integral. Anyone in the chat? Yeah, you're right. Yes, that's correct. Minus infinity to infinity. Yes, of course. Right. If it was Rn, it would be different. It would be different. Wouldn't be as simple. But R, yeah, from minus infinity to infinity, the real numbers. Okay. Now, however, this integral here, you can see that it's some sort of a Gaussian integral, right? Integral of e to the negative x squared. For those of you who have taken or are about to take multivariable calculus, you know what I mean by a Gaussian integral. Okay, because there's a product here that looks interesting. Hint, hint. So now I do have to give you hints if you haven't seen my last live show. At the end of the last live show, I talk about applications of the gamma function in both probability and in physics. This is a physics application. It has to do with something called the heat kernel. Okay. All right. The heat kernel. Has anyone ever seen or heard of what a heat kernel is? Anyone at all? Please let me know. Not, it's okay. All right. So the heat kernel. All right. So the heat kernel, right, it's just a way. It's actually from PDEs when you do partial differential equations and stuff like that. There's something called the heat equation. And it has to do with heat distribution and stuff like that, but also and convection and all that stuff. So we define it as capital K. Okay, so capital K as a function of x and t is equal to 1 all over the square root of 4 pi t e to the negative x squared over 4t. Okay, so there's this product of 1 over the square root of 4 pi t that comes into play. So this integral has applications in thermodynamics specifically. Okay, where you want to figure out your heat distribution and stuff like that. Okay. All right, so this is a very handy integral. All right. So now, as I said, as long as you have some Gaussian integration, you'll find this straightforward. Okay. Anyone want to take a dive at this integral? I don't want to reveal how to do it. I want you, the audience, to give me something here. How do I do this integral? Oh, okay, sorry, just another guy. So that's no problem. Let me go through the process. Okay. So as I mentioned, I already talked about the definition of the heat kernel. K for convection is a function of x position t time, and it's 1 over root square root 4 pi t e to the negative x squared to the over 4t. Okay. Now, in order to integrate this, I'm just rewriting the problem. Right? We're integrating e to the negative x squared all over 4t times k, the convection function as a function of position and time, with respect to x. Okay. And you're right, the limits of integration are from minus infinity to infinity. Okay. Times e to the negative x squared over 4t. K as a function of x and t is 1 over the square root of 4 pi t. Right? This is what I put over here. 4 pi t e to the negative x squared over 4t. Okay, so there's nothing to get confused here. It's actually straightforward. But yeah, if it's your first time, you don't know what I mean. So that's why I had to put this up. Okay, I'm restating some methods and definitions. If you haven't seen them from the last live session, it helps if you keep up with the live sessions. If not, you can always view them after when it's not live, I guess. Depends if you're on and you're seeing them. Okay, so as I said, we're over here now. Okay, so this integral, I substituted the convection function as a function of two variables, position and time. Is that making sense? Okay. All right, so we have that. Now, remember, the question is to find the asymptotic expansion. It's already written in an integral form. So we need to put some use of Laplace's method if possible. Okay, so I made note that it's written in terms of Laplace's method. Okay, so again, I just rewrite my integral from minus infinity to infinity, e to the whole power. Now, this now becomes minus to the whole power of 2x squared all over 4t, right? Because it's very straightforward. I don't think I need to explain how I got that exponent, times 1 all over the square root of 4 pi t dx. Okay, so now we're over here. Okay, so now we're over here. Hopefully you guys are understanding. Yeah, I see. Yeah, good. Excellent. Yes. All right. Glad to hear you understand. So now it's 1 over square root 4 pi t, integral from minus infinity to infinity, e to the negative x squared all over to t, because 2 over 4, the whole power with respect to x. Now, what we got here, okay, is going to be 1 all over the square root of 4 pi t, right? And then that comes out because t is a constant here. We're only integrating with respect to x. Right? So if we integrate with respect to x, everything else is constant, even the variables, times the integral from minus infinity to infinity to negative x squared all over 2t dx. Okay. Now, you probably notice that this is some form of a gamma function. Quite often it's used in probability and statistics for probability density functions and bell curve analysis. Okay. So it's a Gaussian integral, actually. Okay, e to the negative x squared. I think we've talked about the definition. Does anyone know how we go about this? I don't want to show any more detail, but yeah. Anyone know? Anybody at all know how to integrate an improper integral of e raised to the negative x squared power? By the way, this would be handy for a lot of you for your mathematical toolkit, especially for those of you who are, well, a lot of you in STEM need to know integration and series, so my lectures will be handy, right? So this is like really working your integration techniques. So anyone know how to integrate e to the negative x squared? It's a Gaussian integral. As long as you know that, it's be not that difficult. Yeah. You're yeah. You nailed it. Yeah, exactly. U equals x squared over 2t. That's right. Okay. So u equals x squared over 2t. Yeah, exactly. Well, x squared over 2t, you said. Now, here's the thing. What you could do, yeah, I know what you're saying. That's true. But what you also could notice here, right? You can do this faster. You could use u substitution, and then from there transfer it to polar coordinates, right? Right. So you could have said that this integral from minus infinity to infinity of e to the negative u squared, let's say, it doesn't matter what I call it, du, right? This integral right here can be translated into something like this, right? A double integral, right? So a double integral of e to negative r squared r dr d theta, okay? A double integral in terms of polar coordinates, okay? Where r will be bounded from 0 to infinity, and theta will be going from 0 to 2 pi, because theta has to do with the unit circle, right? So the range for theta has to go from 0 to 2 pi, right? Okay, I wouldn't say exactly. I know what you mean. You want to use u equals x squared over 2t. So I just noticed that there's a slight mistake with that, because if you let u equal x squared over 2t, right? So u equals x squared over 2t. Okay, if you do that, there's a bit of an issue here. You substitute u here, you get integral of e to the negative u. You want to get your integral in terms of e to the negative u squared, right? You want it to have it such that it's e to the negative u all squared. Okay. With this, u being x squared over 2t, it becomes a bit of a problem, if you know what I mean. And then the differential will be somewhat of a problem for the du. You know what I mean, right? Just another integral guy, you know what I mean? Like, you want to get it, like this. You understand what I mean? Right? Does that make sense? Right? Because you want to get it in terms of e to the negative u squared du. Okay? Now, once you have done that, I hope you know how Gaussian integration works. If not, I may need to put it over here, like how I'm getting these polar coordinates. Can I skip over, or do I need to show how I'm getting there? You know what I mean? Let me know if you want me to go on the side here and do some stuff, like extra calculations. Okay, yes, exactly. Yeah, I was talking about going to polar, right? I was talking about going to polar. I'll do it. I won't do the whole thing, but I'll show you what I mean, right? It was like I was equal to integral from minus infinity to infinity of e to the negative. Let's say it was the standard form of this, e to the negative x squared, the simple form, right, of dx. Okay, and then after I defined another I as being integral from minus infinity to infinity of e to the negative y squared dy, multiplied them together, I got I squared equals integral from minus infinity to infinity e to the negative whole power of x squared plus y squared. And then it was like, you know, yeah, it was like dx dy. And then after, from here, you needed to get I squared equal to the double integral of e to the negative r squared. How do I know that? That's polar. X squared plus y squared is a circle. E to the negative r squared, r dr d theta. We showed that we got root pi from this after square rooting the I, right? Is that ringing a bell? Just let me know. Hopefully it's ringing a bell. Okay. Right, so that's how we got that. We figured out that I, the integral, for a Gaussian integral is always equal to root pi. However, though, right? Good, you got it, perfect. All right, so it is equal to root pi. However, you do need to be careful. Here we have e to the negative x squared all over 2t dx. Okay. It is root pi, but not quite root pi. I need to put a definition here that's going to help you understand, a fast definition that will allow you to skip over this double polar coordinate type of stuff, right? Because it just takes time all the time to do this. So how do you know that your Gaussian integral will always be, well, will be root pi, or if it'll be something else? Because when it's not e to the negative x squared alone, and it's just e to the negative x squared with a constant, it's not root pi. So let me explain. Okay, I'm putting another definition here. So definition. Okay. So let me explain here what I mean. Given a Gaussian integral, all right, so given, let's say, yeah, I'm going to use blue here. Given a Gaussian integral, okay, Gaussian integral. Okay, let's say I call it I again, doesn't matter. Yeah, I'm going to say I. And I is equal to the integral from minus infinity to infinity of e to the negative a times x squared dx, where a is a constant, right? A is a constant, a belongs to the real numbers, okay? All right, so let me explain. So this is what we have right now. Then what happens, okay? Just one sec, putting a lot of definitions today. Then our I, by the way, this is I squared. Yeah, it's I squared. Then I, after doing this integral and taking the square roots, should always equal to the square root of pi over your constant. Then this implies, I should say, then this should imply that I equals the square root of pi over a. This is always true. This is a definition. It can't be disputed. That's what definitions are. Okay. So anytime you have e raised to some negative constant times x squared, and you integrate, your integral should be the square root of pi, all under the square root pi over a, raise a number. Does that make sense? I just want to check the chat. Make sure you guys, thumbs up, if you can do that, or just perfect, excellent, perfect. Okay, nice. So we got I equals root pi over a. Okay. So given that information, we want to integrate e to the negative x squared over 2t. Okay, x squared over 2t. Think of a in this case being that negative 1 over 2t. The t has to be included. It's a constant. We're integrating with respect to a, so respect to x. So t is a constant, just like the negative 1 over 2. Okay. Anyone want to take a guess how that integral will be if I apply this definition? Anyone take a guess? Root pi over a. Remember, a in this case is this portion here, that 1 over 2t. Let me see anyone. Okay, so if no one's taking a guess, I'll take a whack at it. Okay, so on the next page, okay, so continuation, as I said, I'm just using the definition of the Gaussian integral, right? E to the whole power of negative a x squared is always equal to root pi over a raised a constant. In this case, our integral, remember, we still have our constant in front, 1 over square root 4 pi t, improper integral e to the negative x squared over 2t dx. This should be equal to 1 all over root 4 pi t times root pi over a half, where oh, I almost forgot there's a t there. Did I forget my t? Yes. Yeah, I think I forgot my t there. Yeah. Let me put my t here. T's in the denominator as well. Oh, damn it. I should write it better. 1 over 2t. 1 over 2t. Okay, so I have to put that t factor in. I think I forgot that in the rest of my calculations. Is that making sense? Okay. All right, so that's what we have so far. Okay, so this would actually be square root of 2 pi t. Okay, this would be square root 2 pi t. All right, because I'm flipping everything, right? Pi divided by 1 over root 2t, that becomes root 2 pi t, root 2 pi t, and 4 pi t. The pi t's cancel. That's square root of 2 over 4. There should be a t there. T gets canceled. There's a t there as well. T gets canceled. Square root of all over 1 over 2, which would be 1 over square root 2. Okay, so our final answer should be 1 over the square root of 2. Ah, yes. That's pretty interesting, isn't it? Okay, so our final answer when we have a Gaussian integral is not always root pi. Okay, you need to be careful, right? And when there's constants involved where we have, and not just constants, maybe we had, what if our integral was in the form of e to the whole power of a standard equation, a quadratic standard equation? Okay? We can't just assume that it's going to be root pi. We have to maybe complete the square, maybe do other manipulations. So quite often in mathematics, and this comes up a lot, that's why I'm doing this, the methods are very important. Going through the details, applying certain methods, noticing certain things, connecting things is very important. Okay, so that's exactly what I'm doing here. So 1 over root 2 should be the value of this integral. I hope you guys are understanding. Okay, so we're moving on to research problem number 3 that I assigned from last lesson. And that is the studying the asymptotics of this I of A. I'm just saying I as an integral, define I as an integral as a function of A equals the integral from minus infinity to infinity of ix squared e to the ax squared dx. Okay, let me give you some history and backstory to this, if anyone wants to know. Okay, this integral here is used in quantum mechanics. It's known as a quantum oscillatory integral. Okay, so now I'm going to get you guys into the visual realm of Gaussian wave packets. That's what this integral is, right? Has to do with a Gaussian wave packet. Okay, let me explain. I can either use Desmos or some other type of software. I also make simulations, but today I was lazy, not that I want to make simulations. So maybe next time I'll do a simulation that will look cool from some coding or something. I don't know. Okay, so let's go. Let me get to sharing the screen. Okay, so let me stop share and then just share my screen. Okay, let me just share. Okay, so share screen. I'm gonna share screen. Okay, so let me share Desmos. Where's Desmos? Okay, share it. Okay, so as you can see here, if you're all seeing this, all right, we have a graph of e to the whole power of iax squared. So as you can see, it's a bell curve type of shape. Right? You all know what a bell curve is. It's like grade 11 math, right? Grade 11, well, you don't go into the details of it, but you've probably seen it. It's for probability density functions, more specifically calculating, certain things, properties, mean, standard deviation, away from the mean, nodes, stuff like that, median, whatever. All that stuff comes in handy. So what we're looking at here is an example of a Gaussian wave packet. Okay, so in quantum mechanics, this type of behavior comes along, usually some sort of oscillations, usually in the form of Gaussian curves. So here I've put some parameters involved, right? I put A is going to be a parameter. I don't know if I can say that for I is a complex number here. Let me make sure, am I putting this on the imaginary? Assuming I put it on the imaginary axis. Just give me a sec. This should be accurate. Just taking into play the imaginary axis because I have it to the ith power. I being a complex number, by the way. Okay. All right. So we're looking at this here. Okay. So let's play the model, right? The graphical model here. Okay. That's not. I don't want to show it all the way. Let's say from minus 1 to 1. Is that going to play okay? I don't want to show the whole range upwards. I just want to show some. Come on. 0. See if that's okay. That's okay. The spread is all right. Now, as you can see, it's a pretty cool graphical model here that we have. Right? Our bell curve is pretty interesting. Can anyone tell me the properties of the bell curve? What would be the domain of this bell curve? Anyone know? The bell, like the domain and range, just for curiosity's sake. Anyone know what the domain is? Anybody? Domain, range. Okay, so the domain, right? The domain should be spanning from minus infinity to infinity because that curve here is going from the left end of the x-axis infinitely wise to the right end of the x-axis infinitely wise, right? So there's no like it's unbounded. It goes on from minus infinity to infinity. Okay. What about the range? Range would be from what? What are the boundaries? What are the ranges for that? Anyone know? What would the range be? The ranges will just be something going from 0 to that apex there. Exactly what that number is. 1.5. I don't know what it is. Some 0. Y is between 0 and 1 point something included. My squares there. 0 to 1 point. Yeah, 1 point. No, that's 0 to 1. Yeah, 0 to 1 because every 2 squares is another number. So yeah, 0 to 1. Y is between 0 and 1 included. 0 is included, 1 is included for the range. Are there any asymptotes? It's a good question. Are there any asymptotes? Answer that. Are there any horizontal asymptotes for this function? Since we're looking at the behavior of this Gaussian wave packet. I'll be right back. I have to go to the washroom. Be right back, guys. I have to go to the washroom. So think about it. What are the horizontal asymptotes? Okay. All right, so I'm back. We're looking at, so we talked about the domain and range of the function. Okay, so domain we already figured out what it was. Minus infinity range was going from 0 to 1, right? Y is between 0 and 1 included. Now the horizontal asymptotes to be along the x-axis. So y is approaching, y is equal to 0, right? So that curve never is actually hitting the x-axis. It shouldn't hit the x-axis. Okay, very close to the x-axis, so it's approaching 0, but it's not quite. There shouldn't be there should be an asymptote, horizontal asymptote, unless there's any dispute on it. Okay, let me know if you have any disagreements on the characteristics. Also, for those of you who are just coming in, this is a live show. We're looking at, again, reviewing, and it's a Q&A session on the last problems I did, okay, from my book, Advanced Integration Techniques. Just looking at the last couple of problems, the homework problems that I gave, okay. All right, so guess what? Yes, it is a horizontal asymptote, okay. Okay, anything else we should discuss here on varying the parameters of this function and do some cool stuff? Let's say we had, let me think here, if I varied this guy, 1, let's say if we put it from 0 to 1, just want to see what's happening. No, bad. -1 to 0. I just want to show the wave packet the way it was. Yeah, just showing. My main point was to show a bell curve. Okay. All right. So let's get back. To it. Okay. So stop sharing. I'm going to get back to my whiteboard. Okay. So just give me a moment. Entire screen. I'm showing you whiteboard. Okay. So what it means by studying the asymptotics, okay, it means that we need to do an analysis of the integral in terms of the asymptotic methods I mentioned, okay? Now, we need to understand, here's my 3-pillar approach. It may not look as important, especially when you're given an equation. Especially if you know the mathematical method, you should be able to deduce certain things. You know the method, you know the reasoning, you apply something. However, though, that's only step 3 when it comes to solving a math problem. To solving a math problem, especially when it gets complicated or there's words involved, step 1, always make sure you understand the question. You have to understand what's being asked. If you don't understand what's being asked, even if you know how to do it, you don't go nowhere. So that is step number 1. Make sure you understand what's being asked and you have a foundation in what's being asked. Okay. And then step 2, not always, but quite often, use modeling. Graph what's happening. If you know how a function looks like, graph it. Extrapolate the equation and graph it in terms of its mathematical model so you can see the behavior of what's happening. If you know the behavior of what's happening, in step 3, when you actually have to do the calculations, you will be able to make a comparison. Does my graphical model match the algebra and the computations that I'm doing? If so, you're correct. If not, you've done a mistake. Okay. I hope that makes sense to a lot of you. Okay. That's my unique perspective when it comes to doing these types of problems. All right. Or math in general. It doesn't just have to be applied mathematics. So we're looking at this quantum oscillatory function here. Okay, now it says e to the I ax squared. All right, we can integrate this. Now I said I is a function of a. In reality, there's multiple ways of doing this. You can do this using there's multiple methods. Okay, there's too many methods. I'm trying to decide which one to use. I'm going to use Laplace's. Well, first off, we know we have to study the asymptotics. So we know we have to use one of the 3 methods, either Laplace's method or Stirling's method, one of the 3 characteristics of Stirling's method. Stirling's approximation, sorry. Yeah, so I'll probably go with, since it's an in an integral form, and we're studying the asymptotics using Laplace's method. Okay, just to let you know the definition again, or the method. Right, so method, this reiterating method. Okay, Laplace's method states that if I is a function of s, and you integrate, right? You integrate e to the whole power of negative s of f of x comma t dx, right? That's what the method states. If it's in some sort of form like this, then you just treat the asymptotic. You just do regular integration. Okay. As opposed to doing like approximating, but which is asymptotic, but this is still asymptotic even though we're doing direct integration. Okay. Any questions? All right. So we're going to do this, and we can integrate use one of two ways, either using Feynman trick, because I is a function of a here. In other words, I made the Feynman integral easy because I already positioned where a is. Quite often when you use Feynman trick, you have to know where to position a in order to, differentiate under the integral sign correctly and then integrate again. Does anyone understand Feynman trick? Because I talked about it not just last time, but even in another lecture. Feynman trick. Anyone understand Feynman? Okay, so we're looking at integrating this guy. If I had used Feynman trick, so I use Feynman trick, and there's an a there. It's tempting to use it. Okay, so we have for a. If I did my d by dA on both sides, I'm just going to use Gaussian integral. Okay, by definition. So I'm going to say here by. So I'm going to use definition. So I of a is going to be equal to the square root of pi divided by a. Okay, pi divided by a. And in this case, let's be careful. IA. Okay, I is a constant, a is a constant in this integral here. Okay. However, though, notice how we have a bit of an issue, right? We're getting the square root of this. I is under our square root. Isn't that a problem? Should be. Okay, take square roots of negative numbers, and even if you have, square root of a negative number you can't do, but now this is in terms of I is a square root of -1. If you took the square root of -1, that's just weird. You can't take taking the square root of -1 is a bizarre thing. Okay, so this problem here doesn't have elementary methods that will be able to solve it. Yes, very interesting. No elementary methods to solve it. Because this is also problematic. Assuming if we're in the reals, quite often we're solving things in the reals. Even in the complexes, quite often we want our i's to cancel somehow. Okay, so direct Gaussian integration probably will be problematic, I'm thinking. There's a reason why I have this as a challenge. And also, if you get my book, I have integrals like this. That being said, though, most of them are solved, some of them haven't. And the reason why they haven't is because they're extremely crazy. Only for outstanding students you want to tackle them. They may not even have an open-ended solution. Like they may not have a solution. So they're open-ended. Okay, so that means that they need further research is needed, right? because I'm not, I wasn't smart enough to figure that out. A lot of other people aren't either. So this may be one of those problems, and that's why it's going in some sort of circle. Unless we find a way to integrate under the square root of I, right? Integrating under the square root of I, unless someone can come in here and knows how to do it. Can also use contour integration. I don't want to do that right now. And I do have a lecture on contour integration, but we can use that method too. But I'm just using the most recent methods from the most recent videos, right? Feynman trick, Gaussians, and stuff like that, and gamma function. Trying to see, studying the asymptotics of this would be a bit annoying. It is an improper integral of e to the whole power of IAX squared. Anyone have thoughts? Thoughts on this? You can see that this integral here, as I said, this is the one exception to the rule where the Gaussian integral definition, I'm not saying it's wrong, I'm just saying that it comes somewhat problematic because, well, the fact that it's somewhat problematic means that it may be wrong. I think it is. Because we're getting pi all over IA under the square root. I already is equal to square root of -1, right? We use I already to take care of issues of square roots with negatives underneath. Now we're taking the square root of I, where I is the square root of -1. So we're taking a double square root of -1. Unless we rewrite it in a way that puts it in a more clean and real type of solution, may be a problem. Let me think here. Use Feynman trick. I is a function of A. A is my parameter. My parameter is fixed in the exponent. Differentiate, then I can differentiate both sides with respect to the parameter A. Differentiating with respect to both sides of parameter A means that I get 2ix in the denominator and the constant at front. Not the denominator, when I say 2ix, 2ix in the front of the integral, differentiating 2ix integral from -infinity to, so it'll be 2i. Yeah, I might try that. I might try using, yeah. I think my approach was wrong, going directly into the Gaussian integral. Probably have to use Feynman trick, then use Gaussian integration. Okay, so what I'm going to do is, here's my approach to some sort of solution. It may not end, it may not have a closed-ended solution, but let's try it anyways. Okay, so what I'm going to do is, okay, so we're going to do, if I as a function, I'm going to use blue. Okay, so sorry about that, I as a function of the parameter A is equal to integral from -infinity to infinity of e to the whole power of IAX squared dx. The fact that it's already a function of the parameter means we could use, if we want to, Feynman trick. Okay. Again, for those of you who don't know, Feynman was a theoretical physicist. Okay. Yes, I know what you're thinking. He made a contribution to math. Yes, he did make a contribution to math. It's Feynman trick. It's in my other lecture that I talk about. And it's an ingenious way for calculating complicated integrals. Okay. So I'm using it right now. So I of A is this integral. Okay. Then I differentiate both sides with respect to the parameter. Okay. So let's see if that's going to help us. So di, right? So di dA. Okay. D by dA, right? The parameter both sides, and then integrate from -infinity to infinity of e to the I ax squared with respect to x. Okay. I can move the differential operator inside of the integral. That is completely allowed. There's a definition from Calculus 1. In case you're wondering where that comes, that's a definition. Okay, so integrate from minus infinity to infinity. D by dA of e to the negative I ax squared dx. Okay, I hope that is helping the audience here. Okay, so we have this integral. Now, we have this integral here, okay? What we need to do is differentiate with respect to a, right? What is that derivative with respect to a of e to the ix squared? Anyone know? If I differentiate with respect to the parameter a of e to the whole power of negative ix squared, what is it? You know, everyone's shy or doesn't know. All right, so this is now going to become 2 negative 2i. Okay, so this comes negative 2i because that's the constant. Negative 2ix times e to the negative I ax squared dx. Okay. You'll notice that this simplifies things. Negative 2i can come to the front of the integral because it's a constant. So negative 2i, I like using different colors. So that's why people don't get bored. Minus infinity to infinity. Okay. X e to the negative I ax squared dx. Okay. This is what I have. Now I can integrate this, right? What method can I do? I don't even need Gaussian integration right now. It's not at the moment. How can I integrate x e to the negative I ax squared dx? Anyone know? Okay, it looks like nobody yet that I can tell knows. Thumbs up in the chat if you understand. Thumbs down if you don't. If you're lost, please let me know. I like communication. I don't want to jabber. I want you guys to communicate. Tell me what's on your mind. Okay? Right, for this integral right here. Simple. U substitution, right? Because you'll notice that this can be set to u, okay? And then my du will be a factor of x dx somehow. I'll get the correct differential in order to integrate. So let u equal to negative, I'll just say iax squared, not negative. U equals iax squared. Du will now equal to 2iax. Iax dx, okay. I have that. Divide everything by 2 ia, so it becomes du divided by 2ia is equal to x dx. I left this as a factor. Why did I do that? Why did I have my differential equal to x dx? That's all I need to integrate now. I can replace everything. U substitution is replacing everything in terms of u as long as it's covered. Okay, so now it's going to be minus 2i, and then integrate. Okay, so integrate from minus infinity to infinity. X dx is replaced with du over 2ia, e to the negative u du. Okay. All right. Now, here's the thing. This integral here, let me think, this still gives a problem. Still somewhat of a problem. It's really fun. I don't know what can be somewhat tricky. Getting confused. Where am I into? Anyone lend a helping hand here if you have any thoughts? There's a problem here. It would be a bit of an issue of the integrand inside, because you can see we have it. It's not a Gaussian integral right now. Now it's an integral from minus infinity to infinity e to the negative u, not u squared. So we still end up with a problem. Yeah, this may be open-ended. We don't know open-ended problems. So that means that it doesn't have a problem. We know that there exists a solution, but we don't have one. We don't know what it is. Like, and this will attract, these types of problems are rampant in my book as well. This will attract a lot of researchers or graduate students or outstanding students at younger levels who want to try this problem or problems like this, then this book is for you, right? The open-ended ones, not even I can solve them. But at least they're fun though, but they go in circles because you don't know how to approach them, right? In other words, you can do everything that is, logical by mathematical methods and still end up like, oh, I almost got it. And then you do another method because you think that's wrong. You do another method, you say, oh, I almost got it, but still it doesn't produce the results. This is an example of that. So this is open for interpretation. Yeah. Unless anyone has thoughts on this. Integral d by dA on both sides, and then parameter. Differentiate the parameter of both sides with respect to a. 2ix e to the negative iax squared power with respect to x. And negative 2I in the front. Okay. All right, we'll let this go for now. Yeah, as I said, this is one of these problems. I wouldn't say it's open-ended. Like, we absolutely don't know a solution exists or an open or close to solution exists. But it looks like it's in the notion of that because I've applied everything. Use Feynman trick. Well, first I started off with the Gaussian integral. That didn't make sense because we got an imaginary number inside the square root, which is a bit odd. And then after I used Feynman trick instead, differentiate with respect to the parameter of a on both sides of the integral, doing that using u substitution to try and put it in an appropriate form for the integral. And you can see we get an improper integral, but if I integrate that anyways, let me see. Negative u is iax squared. U is, let me see here. Just 1 second. No, something is a bit paradoxical here. Because the I is on the outside. I is on the outside. And then well, it's not the I that's the problem, I'm saying. The problem is that the integral is not looking appropriate for Gaussian integration. The point was to use Feynman trick and then apply the Gaussian integral. Hopefully it being in the form of integral of e to the negative u squared du, but we're not getting that. Let's see what has thoughts. You have thoughts on this? Yeah, we're going to have to leave that. Yeah, we may have to leave that unless something happens here because I already integrated that. U. e to the negative u, that'll give me e to the negative iax squared. Yeah, something's a bit. So this one requires, so I'm going to assign this. Let's see if I can solve this. So I'm going to put here requires further research. Requires further research. I mean, you can take it down as a problem if you want to challenge yourself. Further research. But this can be a bit nasty. Okay. So anyone want to take it down as a challenge problem, go right ahead. But we're going to be moving on, okay? Because I have to move on. I have to move on to the beta function because I've taken up practically all of those assigned questions I talked about last time, in the last live lesson. Okay, so we're moving on, I think. Yeah, we have to move on. Okay. All right. But you can always, for anyone who wants to try this for homework, do it. And if you get any results, you can send an email to www.stem1online.com. I'm curious on what the solution is. Okay. All right. All right, so after the beta function, okay, so we're going to the beta function now. So the beta function is the last function we're going to look at. This is the main part, one of the main parts in our understanding of this lesson. I've talked about it before, but this is going to be more proof-based problem solving, okay? Because my book has both the computational side, but also a rigorous proof side as well. Okay, so it's a mixture of both. A balanced mixture, actually. So we're looking at the beta function, okay? So let's look what the beta function is. We have to define what it is. Okay, so I'm putting up a definition for those of you who don't know. By the way, anyone coming in, again, this is a live session. It's on, it's pretty much a Q&A night. It's office hours and research problems on my book, Advanced Integration Techniques. Okay, just letting people coming in that this is office hours. All right. Okay, so the beta function, definition 1, beta function is defined as capital B of x comma y. And this is an integral from 0 to 1 of t, all to the power of x minus 1 times 1 minus t. Doesn't matter. It could be any variable, right? I'm just using t here. All to the power of y minus 1 with respect to t, where both x and y are, so be greater than 1. Okay, and their exponents. Okay, so that is the integral form of a beta function. All right. I think that is straightforward for anyone who has questions. Okay. All right, so we have that. Then we have definition 2, the gamma beta identity, which states that we can calculate the beta function, which is this integral, any integral written in this form. Okay. Integral from 0 to 1 of this product with respect to t. Any integral can be calculated using the gamma beta identity. Okay, so the gamma beta identity is capital B as a function of x and y, is the product of the gamma functions x and y divided by the gamma function of x plus y. Okay. Is there any questions? Let me know. Okay. All right, so no one yet. Where gamma of x is the gamma function. Okay. Or gamma of any variable, x, y, or gamma of x plus y. It's some gamma function of some variable. Okay, so again, this is the way to calculate the beta function integral that I have above here. It will be an asterisk. Okay, so knowing this, we have a problem here, and it's a proof. Okay, so those of you who love proofs, I hope you're staying tuned. Okay. So problem 1, by the way, proofs is a good way to develop your mathematical intuition, which is what this channel aims to do. Okay, so prove that the beta function of a variable p and q plus 1, or p and q, or some exponents, let's say, divided by b, the beta function of p and q, is equal to q divided by p plus q. Any ideas of how to solve this? All you need to know is you just need to know these definitions. And you have to understand what a gamma function is. Okay. Right. Hint, hint, gamma function is related to a factorial. And so what I'll do is, no one's coming in, I'll keep going. B as a function of p comma q plus 1 over b of p of comma q, okay, is use the following. Okay, so here I'm going to attempt this by doing the following. Okay. We know that the beta gamma identity is the following, right? So let's say I'm going to call b as a function of, put over here, b as a function of p and q is gamma of p times gamma of q divided by gamma of exponents p and q. Okay. Now I'm looking for gamma of p comma q plus 1. Replace every q with q plus 1, right? So p of p comma q plus 1. This is now gamma of p times the gamma of q plus 1 divided by gamma of the addition of the two exponents, p plus q plus 1, it should be. Okay. All right, so that's our expression. So a beta gamma identity. Okay, so b as a function of p and q plus 1 is now reduced. Gamma of p, that's equal to p minus 1 factorial. Okay, q plus 1 bracket is equal to q plus 1 minus 1, all in parentheses, factorial. Okay. Right, it's just n minus 1. N minus 1 in parentheses factorial is the gamma function as a function of n. Okay, for whole integer values. That's what that definition is for. For whole integer positive values, you use the gamma function of n is equal to n minus 1 factorial. Okay, if that's understood. All right, then from here, I take gamma p plus q plus 1. This becomes p plus q plus 1. Okay, right, that's my n. Minus, okay, what should I minus here? Remember, it's n. Gamma of n is equal to n minus 1 whole factorial. This here should be my n, and over here will be 1. Okay, so minus 1 factorial. Okay, so from calculating b of p comma q plus 1. Okay, so now it's going to become b of p comma q plus 1. This is now p minus 1 factorial q factorial. This reducing this. Okay, p plus q plus 1 minus 1 gets canceled. That becomes p plus q. Okay, so now we have the p minus 1 factorial. So I figured out my expression here, b of p comma q plus 1. All right, so that's what we have. Then from here, calculate b of p comma q. We know what b of p comma q is. Right, so now we're going to do the bottom. So next, B of P comma Q, since we know this is just the definition of gamma of P gamma of Q divided by gamma of P plus Q. Okay, so this is now B of P comma Q. Gamma of P is P minus 1 factorial. Gamma of Q is Q minus 1 factorial. Minus 1 factorial. P plus Q. This would be P plus Q. P plus Q minus 1 factorial. Minus 1 factorial. Okay, so that's what we have. All right. That means, how can we get the ratio to be Q over P plus Q? Well, now we just divide them. We have the expression for both, substitute them in and divide the ratios. Yes, gamma beta of P comma Q plus 1 of P comma Q plus 1 divided by B of P comma Q. This gives us P minus 1 factorial. Yeah, P minus 1 factorial. Factorial. Q factorial divided by P plus Q. Yeah, divided by P plus Q. Is that what we're dividing? Yeah, that one first. Divided by B of P comma Q. Divided by P of P comma Q. Let me make sure if I have everything in order. B of P comma Q plus 1 plus 1. B of P comma Q plus 1. P minus 1 factorial. Q factorial divided by P plus Q. Then divided by B of P comma Q. P minus 1 factorial. Q minus 1 factorial divided by P plus Q minus 1 factorial. Okay. And then from here, right, what we're going to get, right, the P minus 1s will cancel. Guess 1 factorial gets canceled. Q factorial divided by Q minus 1 factorial. That just reduces it down to Q. Okay, so Q here. Q factorial and Q minus 1 factorial. That just becomes Q by Q minus 1. Q minus 1 factorial is Q minus 1. Yeah, so Q all over P plus Q over P plus Q minus 1 factorial Q over P plus Q. So we just proven it. Okay, so here's the proof. All right. Okay, so that's how we do these, some of these. Look at another one over here. I'm not going to do all these. These are going to be for you to take home. Okay, so if anyone wants to try these, right, I'll give hints right now. Okay, so there'll be hints involved on how to maybe do this. Okay, alpha. So this one here, right, problem 2 from the challenge problems from the proofs. So we're taking the limit as n approaches infinity of n to the alpha power, the beta function of n comma n. Okay. Hint. I'm going to put a hint here. Okay, so hint. Actually, I might have some time to solve this. Let's do this right now. So the limit as n goes to infinity. of n to the alpha, b of n comma n. Let's use the beta gamma identity, right? It states that gamma, this will be gamma of n times gamma of n divided by gamma of n plus n, right? That's the beta gamma identity. Okay, so now we got, that's understood by the audience. Hopefully it is. Okay, so now we have that, we have this limit. Then it's going to be the limit as n approaches alpha, gamma of n all squared. Okay, all squared here, because gamma n. And then in the bottom will be divided by gamma of 2n. Okay. And then here's the limit as n goes to infinity of n to the alpha. Right, so n to the alpha, gamma of n all squared. Let me see here. And this will be n minus 1 factorial. This will be n minus 1 all factorial, because that's what gamma of n is. All to the power of 2 divided by gamma of 2n will be 2n minus 1 factorial. Now here is the annoying part. The annoying part is to evaluate the limit. Okay. Yeah, so as you can see, some of these problems are getting more annoying. Trying to evaluate this limit using elementary methods won't work. Maybe since it's a fractional function, L'Hopital's rule might work. If those of you remember from like really elementary calculus, like in high school, using L'Hopital's rule can work as long as you have f of x over g of x, where g of x cannot equal to 0. You can take the derivative of the top individually from the denominator. Okay, so that might be one way to do it. Okay, but I'm lazy. I'm going to leave it up to you guys. I want your input on these problems. Okay, so try doing this for homework. Homework. Do this for homework, please. Okay. All right. Let me see if we're on track on stuff. I can't remember. Okay, where was it? Okay, I think that's all that's left of the beta function that I want to extrapolate, like I want to talk about. We don't need to go into other things about it. I think we've exhausted it enough. One last thing I can talk about are the applications, okay, where the beta function is applied. Okay, the beta function is applied all over the place. It's applied in probability and physics, specifically thermodynamics, probabilities, density functions, Dirichlet integral, statistical mechanics, all sorts of stuff. Okay, so the beta function will be handy for those scientists out there who need a mathematical method to evaluate high-end physics. Okay, so this mathematical method is handy. All right. Okay, so that's what we've got here. Okay. But yes, let me see what else is on the list. On the list for today. Anyone else on the list? Just 1 second. Someone commenting anything? See if anyone else is coming in. Not at the moment. I guess it's getting a bit late. Okay. All right. So let's see here. Talk about that. Okay. So as I said, ask me anything in terms of, any PDEs, Fourier transforms, quantum field theory that's related to these problems, because we're talking about the applications now. At least the application side of the math here. Okay. So if there's no Q&A, that's fine. Please do recommend something, but as I said, this is office hours, right? So take advantage of any questions you may have on the gamma and beta functions, pretty much. Okay. Let me see here. I wanted to look. Yes, there is one more problem that I'd like you guys to do for homework, or if anyone sees this live show after. Sometimes live shows don't always have people come in, or not as many people, and then there may be people after who have seen the live show. It can be a time discrepancy of some sort, so they weren't able to see it but still interested. Anyone after, tackle this problem here, problem number 3. Okay, so the asymptotics, again, the asymptotics of a beta function. So now we're going to apply what I said earlier in the lecture about approximations and asymptotics, but we're going to apply not just the gamma, but also for beta functions. Okay, so find an approximation of b of p comma q where both parameters are large. Okay, so try doing that for homework. And if anyone sees this, these ones I will not take up like I did with the gamma functions, because on Sunday I'm going to move on to a different topic. But you can send it to my email. I'll be interested in seeing what you have to say, what your thoughts are on these. That'll be great. So please send any questions either in the chat on YouTube or send direct email to the website. Okay. So I'd be interested in that. But other than that, I think we're done. Let me see here. Let me think. Unless there's anyone else here, because we're just about to finish. Okay. So as I said, right, everything we did tonight, the gamma function, the beta function, any of these, Feynman trick, all that, yeah, all this stuff, if you want to learn more on it, comes from my book, Advanced Integration Techniques. It's available in the link below in the description to my website. So if you're interested in learning more on these integral methods, mathematical methods in general, then my book is the place to go to. Okay, it will be in the link below in the description of where to purchase it. I'm trying to think if there's anything else. But yeah, if you want to learn really how researchers think in terms of doing advanced integration, then again, the link will be in the description below. Okay. What else? Or if you just want personal help, if you want direct one-on-one help, I offer like one-on-one help in terms of learning these advanced methods, math, physics, specifically, let's say PDEs, partial differential equations, integrals. Let me think. Integrals in terms of maybe Fourier transforms, Gaussian integrals, gamma functions, things that we were talking about so far, right? Or just research coaching. You can apply for tutoring at my website, www.stem1online.com. Again, the link will be in the description at the end of this live show. Okay? All right? And trust me, I'm an expert in these areas. There's not a question you can't ask me and I won't be able to fit. I know it very deeply. Okay. So again, I work with undergraduates and even to some degree, some graduate students, not entirely, but because some of the stuff ends up teetering into graduate school. Okay. And researchers around the world who need help with this stuff. This is the place to be. Thanks for an amazing Friday night, and I will see you I'll try Sunday. Usually my schedule is Sunday, Wednesday, Friday. Sundays at what's the schedule again? 12 p.m. Eastern. Wednesdays 8:30 p.m. Eastern. Fridays 7:30 p.m. Eastern. So far, it seems to be working. Okay. So again, if you need help with either tutoring or you want to learn more about my book, the description will be in the link below. Okay. Have a great Friday night, guys. This was an amazing live show. There will be plenty of more interesting problems and topics to discuss in the realm of applied mathematics and physics. Okay. Have a great day. All right. Bye-bye.